Hello. In this module, we're going to cover the PC model, the phase change model. A phase change fluid means when you have a fluid that can turn into vapor, a liquid going into vapor or vapor going to liquid, phase change is allowed by this model. So we start right away with a thought experiment. What is the experiment we're going to do? Let's say we have some water in a piston cylinder device. Liquid water, everybody is familiar with that. And what we do, we start putting it, this is a resistance heater. Let me put it in red. So is the experiment clear to everyone? We want to heat up some liquid water and observe how its state changes. Why did you put a piston here? Because by putting a weight on the piston, we can control the pressure inside. You can draw a free body diagram of the piston and figure out the pressure inside the piston cylinder device. So now, also this resistance heater is connected to an electronic circuit that we can just put just a desired amount of energy every time. So what we are going to do is to put energy into the system and observe how it evolves. We also know from the state postulate there's just two out of all the thermodynamic properties, P, T, V, U, H, S, are enough to describe the equilibrium. So we can choose any two in a coordinate. For instance, I can say, let's simultaneously do a T. Suppose temperature here and specific volume here, or temperature here and entropy here. If we can locate the values of, say, temperature and entropy, or temperature and specific volume, or temperature and entropy, we can locate the state. We could choose other coordinates, but these are, as it will turn out, the TS diagram would be used all the time in figuring out properties of a phase change fluid. Okay, so let's say arbitrarily we decide this is some liquid. Obviously, V for a liquid is inverse of the density. Remember, density of water is about 1000. So therefore, V is about 1 over 1000, approximately equals 0.001. So it's a very small number. And temperature, let's say we start with 30 degrees Celsius, and let's say the pressure is 100 kPa. In other words, the weight we put is 0, because outside pressure is typically 100 kPa. So let's say we arbitrarily select a state. We say, let me use the red, maybe blue color. So let's say this is my state in the beginning here, and we just choose a number here. I mean, we don't know where it belongs because we don't really have any numbers on the axis. So let's just assume the beginning state is here. Water is at equilibrium. We put a little bit of energy now. Now let's think it out. Just a little bit of energy. What will happen? What will you observe? You'll probably observe the temperature of the water will go up. By the way, when you put some energy, we make sure that this thing is insulated. In other words, there is no heat loss or heat gain anywhere. So this is an isolated system. After we put some energy, we isolate the system. So we put a little bit of energy and wait until the water comes to a new equilibrium. Everybody would agree that temperature will increase. So let's again use the blue color. So this point, the state will now be slightly higher because the temperature may have gone from 30 degree to, say, 40 degree. What will happen to the specific volume, do you think? Well, if you think about it, if we use an SL model, we will say specific volume is almost constant. I mean, is a constant in SL model. But in the PC model, we allow thermal expansion. So can you see right off the bat that PC model is a better model, more accurate model, because we allow the expansion of water. Well, that means what? The specific volume is going to increase a little bit. Recall what is specific volume. It's volume per unit mass, right? Everybody remembers that. Okay, our mass is not changing, so therefore specific volume is going to increase slightly. It's so slight actually, it's almost look vertical. But let's exaggerate that. Let's say the state comes here. And over here, what happens in the TS diagram? TS diagram, okay, I exaggerated a little bit too much. Let's say here. Okay, in the TS diagram, temperature again will increase. What will happen to entropy? If you recall, for a liquid, entropy depends on temperature in a logarithmic way if you use the SL model. So of course, if temperature increases, entropy will increase. We know that also from the fundamental physics of entropy, because if temperature increases, every molecule has more ways to store energy, and therefore the number of ways in which energy can be stored increases, and that's why entropy increases. But a better way to figure out, if you think it's a liquid anyway, so if you look at a liquid and use the SL model, that will give you a guidance at least. Of course, the PC model is going to be more accurate, but we can calculate the entropy exactly, and then we can plot it here. Or suppose we could measure entropy, but we agree that entropy will increase, and it will probably increase. This increase will be more than how the specific volume will change. Okay, so let's continue this experiment. What will happen soon? The liquid will soon reach a point when it's about to boil. Well, let's draw that point with a red color. Let's say right now, when it comes to this state, the liquid is about to boil. That's a very special state. That's called a saturated liquid state. And it's represented by the letter F. This is a special state. We'll call it the F state. Well, the reason we call it F is come from German word fluid, I think. Because the Germans came up with this whole concept of the TS diagram long time ago. So, at the F state, the liquid is about to change its phase. So, it's called saturated liquid. So, let's write down the new terms that we are learning. You heard the word saturation from chemistry also. So in this case, think like, all these bubbles are about to get out of the water. So now, if we add even a little bit of energy, what will happen? By the way, as saturated liquid, by look, you will not see any difference. It's just hot water. And everybody knows at 100 kPa, what will be the temperature, you think? It must be 100 degrees Celsius. Would you agree? This temperature might be 100 degrees Celsius because we are talking about 100 kPa. Now, if we add any little energy, what happens? When water starts boiling, you know that the temperature doesn't change. If the pressure remains the same, and in this case, pressure is always 100 kPa, then temperature is not going to change. But as the vapor bubble comes up, the diagram will look like it'll go up there, and now there'll be bubbles here. Does it make sense? And every little liquid, when it becomes bubble, it expands tremendously. The density of vapor is way, way less than density of liquid water. It's almost like 1,000 to 1. Air has a density of 1 kg per meter cube, and water has a density of 1,000 kg per meter cube. So imagine the expansion. So therefore, V will increase tremendously. Let's go back to again our blue color. But temperature will not change. If we continue this, a time will soon come that all our liquid has just become vapor. So we have just vapor everywhere, no liquid at all. Piston is now up here. And let's consider that just the last drop of liquid just vanished. And that becomes a special state. You know why? Think of this. Now we have all vapor, but suppose we could take a little energy away. That means what? Immediately liquid will appear again. There'll be condensation. So this is called saturated vapor. And this is given by the symbol here called the G state. G for gas. So this is just the counterpart of the F state. It's called saturated vapor. So look at our experiment. We are moving horizontally, and now it's all vapor. Now what happens if we add some energy, a little more energy? It's like a gas, it's like a vapor. What will happen now? Of course, temperature will increase and volume will increase. It's like a gas. You can use the ideal gas law that you learned in chemistry and figure out kind of what goes on to get a guideline. So if I use blue color again, this time things will go up, and there we have it. So if we connect these states, this is the knee-shaped diagram, and this is the locus of all the states at a pressure of 100 kPa. See if that makes sense. So what we have done is wonderful. Look, think of what we have done. That means if you have H2O at a pressure 100 kPa, you know the state is going to be somewhere along this line. If it is on the left side, on the left branch, that means it's a liquid. If it's in the middle part, then it must be a mixture of liquid and vapor, a mixture of F and G states. And if it is on the other side, on the right side, it must be a total vapor. Well, we'll put some more terminology soon, but try to understand what will happen now if I repeat this experiment at a higher pressure. This time, suppose there's a big weight on top, pressure is increased. Well, first of all, you immediately know that probably the whole thing will repeat itself. There'll be similar knee-shaped plot, but you also know if the pressure is higher, water boils at a higher temperature. Any fluid boils at a higher temperature if the pressure is higher. So you know that from a pressure cooker, for instance. So a pressure cooker, we cook by increasing the pressure faster, because if pressure is higher, the boiling temperature is higher. You can also figure it out point by point. I mean, for instance, you can notice that suppose you take our initial state that we started with, and you say, pressure is very high. So you can see that the specific volume will be slightly lower, because probably the fluid will be squeezed at higher pressure. And you also know at higher pressure, entropy will decrease. So in other words, if the pressure is higher, then you can show that the line will be something, the line will look something like so this is a higher pressure line, and again this is the F point and this is the G point, F point and G point for that pressure. This might be 1000 kPa. Now, if we keep on drawing all these constant pressure lines one after another, we do thousands of experiments, and then finally we join all this F point together, then this is the shape that shows up. And all the G point together, this is the kind of shape that shows up. A dome shape that shows up both in TV diagram and TS diagram. We'll just consider TS diagram from now on, because as you can see, they are very similarly shaped, and try to understand things. So just to take a look at that, so let's go over again. What does the dome shape mean? that is, immediately it's become clear that inside the dome we have a mixture. Is there a different color? Okay, this is a mixture of liquid and vapor here, right? On this side we have liquid, and on this side we have vapor. Would you agree immediately? So look at the simplicity. This is called mapping all the states. So if you have H2O, or for that matter ammonia, or any other fluid, say refrigerant 134A, then you know that there will be a dome shape that separates the liquid from vapor with the mixture inside. So let's draw a TS diagram from scratch now and try to understand these different phase compositions with a little more detail. So the first thing to draw a TS diagram is to draw the dome shape, almost a symmetric line. This is T, this is S, and then draw a sample constant pressure line. Suppose and this is known as the F state, just to always remember, and this is known as the G state. So we're going to come up with some more definitions now. Well, first of all, we recognize that on the left side is liquid, on the right side is vapor, but there's some special name for that. So the liquid is called subcooled liquid, and the vapor is called superheated vapor. This is called superheated vapor, and this is called subcooled liquid on this side. The mixture basically means a mixture of liquid plus vapor, which is let's just put it as mixture so that you understand. We'll come back to that. There is also this particular temperature, the boiling point, has a special name. This temperature we'll normally call it boiling point, but if you think about it, if I have some saturated superheated vapor, I cool it down, then I'll probably come down along this line at this particular pressure. Suppose we don't change the pressure and we keep cooling down, we'll come down and we reach the G point, the saturated vapor point. What does it mean? Now if you cool it even a little bit, a liquid drop will appear. So if the state is somewhere in between, it's important to understand that it's a mixture of, some part of it will behave like F and some part of it like G. It's a mixture of these two different states, mixture of liquid and vapor. But they're the same temperature. So what should we call this temperature? Instead of calling it boiling point, which simply means a liquid going to vapor, or somebody can call it a condensation temperature, vapor going to liquid. But think about it, it represents the temperature of every state in between F and G, including F and G. And what is the common characteristics of all these states? They are mixture of liquid and saturation. There's a saturation mixture of liquid and vapor. So this temperature is called saturation temperature, T sat, at a given P. So that's how we'll represent that. You also note that the red line is a locus of all saturation state. Now suppose the pressure keeps increasing, then the knee-shaped plot will go higher and higher. A time will come when suppose the pressure is such that it goes like this. This is a special pressure. First of all, it touches the tip of this dome. What is that point? Is there an F or G point? They meet there, as you can see. So at that point, is that a liquid or is that a vapor? Well, that's called a critical point, CR. It's neither a liquid nor a vapor. Nobody knows how to define it. It's just called the critical point. And that's a very special point. All the properties there are called critical properties. So this pressure will be called P critical. So based on this pressure, there is another kind of division of what do you call the phase mixture, the phase composition. So any fluid that is above the critical pressure, which means anything here is called supercritical fluid. So when you hear the word supercritical, they're all here. The funny thing is that if the pressure is higher than critical pressure, you can see that there is no knee shape. So any pressure here will just continuously, the liquid will become vapor. There is no fixed temperature, the saturation temperature that we just covered for the phase transformation. Now, in that case, how do you define which is liquid here and which is vapor here? Well, because there is no clear-cut definition, but what we do is we take this critical temperature, the temperature here is of course the T critical, and anything above T critical is called supercritical vapor. So this will be called supercritical vapor, and this is called supercritical liquid. As V is for saturated, superheated vapor, and SL subcooled liquid. And of course, M is saturation mixture, that's called, but I'm just calling it mixture. So we have introduced what is known as phase composition. So if you have H2O or any phase change fluid, it has to be one of those five. The composition has to belong to one of these five zones. It will turn out that for most practical problems that we'll encounter in thermodynamics, engineering thermodynamics, will be either in the subcooled liquid, mixture, and superheated vapor zone. Supercritical states are rare. These days there are more use of that, but we'll probably avoid most of supercritical vapor analysis. So mostly a state for us will belong either as a mixture or a subcooled liquid or superheated vapor. And that should be our task now. How do we figure out the properties given? How do you figure out the properties now that we know that the phase composition can be so different? We'll do it in the next section.